Okay, we're ready to get started. So first thing first, you have your first midterm exam next Monday. So I posted this announcement on Brainlearn, so you can find that announcement. Well, in short, you will be taking your exam in different room depending on what is your UID ends on. So if your UID ends on an even number, that is 02468, you go to, well, you stay here. If it is an odd number, like 13579, you go to the Fuller Museum. So write that down and make sure you went to the correct room for the exam. We will switch that for your second midterm exam, so it's more fair. And what to expect on the exam? Well, it is open book, open note. So anything on paper is fine. You can use whatever notes you want to print it out. You can also use your textbook if you like. And make sure to have your own equation sheet and also like constants and everything ready. Your TA might be able to help you. For example, if you forgot like just one constant or how to convert between units for one specific question, but it's really up to you. Like you don't want to waste your time, like raise your hand and wait for the TA to check that number for you. So have those numbers ready on your own formula sheet. Will be very helpful. And again, the process of preparing that formula sheet is a way to study for this course anyway. All right, so have your own formula sheet ready. And well, it's open book. Anything on paper is fine. So no electronic devices. And for this exam, we have 5 multiple choice and 5 true and false problems. So I have one question on the discussion board. So your multiple choice and true and false will pretty much be conceptual questions. There might be calculation involved. For example, if we ask you to calculate molecular weight, I don't consider that to be a hard calculation you have to do, right? So the first 2 are just make those answers. You don't have to explain what you're doing. But make sure you put your answer in the box. So you will have a little box to put your answer in. What we do is we scan your exam in and we just look at that small box. So if we don't find anything there, well, that's unfortunate. So make sure you follow the direction. The section 3 will be 4 short answer problems. So those short answer problems will be like a straightforward calculation or something that you just quickly explain something. So it's short answer problems. You shouldn't take more than 5 minutes on each of those short answer problems. And then section 4 and 5 are comprehensive problems. So that means multiple part problem like your discussion worksheet or some of the longer example we did in class together. All right, and I surveyed about what to cover today on the discussion board. I only got 2 replies, which is a little bit hurt, but nevertheless, I got 2 suggestions. One is to go over different thermodynamic processes and how to calculate delta G, delta H, and etc., and also do a derivation problem together. So we'll do that today. Just in the future, if you have some like quick question you're just confused about or you're not sure about, just post something on the discussion board. Your TA and I actually check it pretty often. Well, at least I check it every morning around like 9 to 9:30. But if nothing is there, I'm just gonna leave. So post something on the discussion session for a quick question is gonna be helpful. Okay, any questions on the administrative side for the exam? Nope. Okay, sounds good. So let's get started for today's lecture. We will first go over a list of midterm 1 topics. It's not going to be the full comprehensive list. These are just the highlights that I feel like I might want to emphasize a little bit more. So again, it's from your textbook, right? From your the first chapter all the way until chapter 3.4. So that's what we cut off from our Wednesday lecture. So make sure you refer to the textbook for the full list. So here's just a personal addition of some of the topics. And then we'll do 2 problems together. One is calculation of like different state functions or heat and energy, heat and work for different thermodynamic processes. And one is on example 2.35, which is a heavily derivation problem. So let's get started. First thing, topics of midterm 1. So let's get started from chapter 1. That's in our lecture 1, when we go over some of the thermodynamic concepts, some of the concepts in thermodynamics. We have been using these concepts pretty extensively during the lecture and also in your problem set. So right now, I highly recommend you look at these concepts and make sure you fully understand what each term means. So for example, when we're talking about system and surrounding, right, you have 3 different sets of description you could use. Like open versus closed, that basically tells you whether or not you have material transfer in between the system and surrounding. Isolated versus non-isolated, now that is a different one. Isolated basically means your system not only not transferring material, it also does not transfer heat. And non-isolated, you can have a system that is closed but non-isolated with something involving like a thermally conducting wall separating the system and the surrounding. And also you can have homogeneous and heterogeneous, like remember our example on the ice water, water and then iced soda water. So that's the idea of homogeneous versus heterogeneous system, and how many phases are there in the heterogeneous system. Likewise, we have different type of wall that we will be talking about. Like you can have rigid versus non-rigid. So a rigid wall just basically can imagine it's not moving. A non-rigid one can move around, and well, you can imagine the volume of that system changing. Permeable versus impermeable, so that's talking about whether you have material goes through that wall. And adiabatic versus thermally conducting. So adiabatic means no heat transfer, Q equals to 0. And thermally conducting, you have some kind of heat transfer. So these are like things that sound straightforward, but you want to make sure like you look at it, you can immediately link that to a specific scenario in your mind. Equilibrium, that's the same idea. Mechanical equilibrium, that's linked to whether or not your system have a acceleration. So for example, if it's like moving, accelerating, then it is not at mechanical equilibrium. Material equilibrium is basically saying, is the material changing, right? For a chemical, is there a chemical reaction taking place? Or is there like, is your water vaporizing right now? And also thermal equilibrium means like, by inserting an adiabatic wall, does it change anything to the system? And if all 3 of them are satisfied, we're saying they're at thermodynamic equilibrium. So far for our system, we have been assuming mechanical equilibrium and material equilibrium. So basically for everything we covered so far, we're saying, okay, it's a closed system and at rest, no external field. So that tells us, okay, our system is at mechanical and material equilibrium. And we're just looking at the thermal equilibrium right now. After your midterm 1, when we start talking about chemical equilibrium and introducing the idea of chemical potential, then we're talking about material equilibrium after midterm 1. But these are just introduction to concepts. All right. And then we went over and started talking about functions. You have state function that are path independent. You also have line integral that are path dependent. And among your state function, you have extensive state function, like for example, you have mass or energy. That's depending on how much of that material you have, that value will change proportionally. Or intensive state function, like, well, temperature, pressure. These are the things we don't care about how much substance are there. All right, so in this case, for example, if I give you a random function, tell me whether or not it is a state function or a path-dependent line integral. So you have to know that. For example, if we say entropy, so that is a state function, and it is extensive. And likewise, when we have something like work, now that is a line integral, right? So work depends on the path you're taking, it might be different. Or something like temperature, pressure, these are intensive state functions. So one of the ways to practice for this kind of problem is just write out all the functions we have talked about and just like look at it and assign whether it is a state function, extensive or intensive, and whether it is a path integral. Just practice it yourself, then it's very helpful. And at the end, we quickly mentioned the idea of equation of state. We went over one of the equation of state, which is the ideal gas law. The equation of state just tells you the relationship of that specific substance well, the relationship of the macroscopic properties of a specific system. So naturally, what we're talking about is relationship of pressure, volume, temperature, and number of moles, amount of substance. All right, at this pace, okay, okay, sounds good. Next topic, we went over the thermometer temperature. So basically how the thermometer temperature is being defined. The actual definition of temperature will change along our way of this course. So far we went over the thermometer temperature, where you're talking about how your mercury expands in that thermometer. And one of the questions here is think about why liquid water is not a good candidate to make a thermometer. All right, and the quick answer here is your liquid water actually contracts between 0 to 4 and then expands from 4 to higher temperature. And that property makes it invalid to build a linear relationship between temperature and its volume. And then we have the idea of the mole. This is one of the subjects that everyone feels like, oh, I know it. It's so straightforward. But if you ask a little bit more detail, then you'll find, okay, I actually don't know that well. So let's use water as an example and do this together. So what is the molecular weight, molecular mass, molar mass, and mole fraction of hydrogen and oxygen in water? All right, so let's do that together. So this kind of calculation is what I mean for like multiple choices. It's super straightforward, and I don't consider it a calculation. So molecular weight is the same idea as relative molar mass. So it's a relative number. It is unitless. All right, we're talking about what is the relative weight of this molecule. So in this case, that means for water, we have 18 without any units for the molecular weight. Now for molecular mass, then this one is talking about the actual mass of one molecule of water. So in this case, molecular mass equals the mass of one molecule of water. So it will have a unit. So in this case, its unit is AMU, atomic mass unit. All right. And then you have molar mass. So molar mass is talking about how much mass this molecule, this substance has in 1 mole of the substance. So if this one we say it's M, this one is M divided by its number of mole. So that gives you to be 18 gram per mole. All right. And moving on, when we're talking about mole fraction, we're talking about what is the relative fraction of these elements in the molecule. And also you can have you're calculating it by the mass of each element in that molecule. So in this case, when we're looking at the mole fraction, you have this one should be mass fraction, sorry. Well, we have the 1/9 for hydrogen and 8/9 for hydrogen. All right, so this one is just a quick example in okay, the mole is a concept that everyone thinks they know, but make sure you actually know what the question is asking about. Okay. Next up, ideal gas. So know how to derive the ideal gas law from the Boyle's law and Charles' law. So again, we scientists, we live in a world that you have to have some kind of experimental results to lead to those more abstract laws. So in this case, we derive the ideal gas law together in class using the Boyle's law and the Charles' law. And when we're saying something is an ideal gas, what we say is there are no intermolecular interactions in that gas mixture. And your ideal gas has other properties, like for example, it's only its internal energy is only dependent on the temperature and etc. Okay. All right. And then comes to the point of calculus. So calculus is something that I feel like lots of people, you have different level of background. But for this class, again, we don't expect you to solve like super, super complicated calculus problem, but you have to know the fundamentals. For example, if we're taking the derivative of something like x to the n, you know, like, oh, you put n to the front and then x n minus 1, right? So in this case, if this x to the n is x minus 1, or like 1 over x, you know that d x1 equals to minus x squared over 1 dx. So something like that. So know how to solve these basic integrals. There are also some of the rules that we will be using, like these are the things. For example, if you're taking the product of two different functions, you're taking a derivative of that product, what you're actually doing is, well, u dv plus v du. So typically you see that as like d pv, and that's equals to pdv plus ddp, right? And the chain rule is something that can help you to solve calculus problems, and we also use it occasionally. They know how to write the total differential of a function from its partial derivatives. And in this case, you have like dz equals the partial derivative of z over r at constant st, dr, and et cetera, et cetera. And one thing that I don't think I emphasized, but we sort of used, is the relationship between partial and normal differential. So when we're writing something like a partial differential of z of x, so z of partial differential of z over x at constant y, it's the same idea when we write its normal differential. So on the left-hand side, in those normal differential, the subscription y just tells you, okay, so these are the number that's being measured at constant y. So these two terms are just the same equivalent terms. So that's the link between your normal derivative and partial derivatives. Yes?
Have we used the total differential in anything we've covered so far?
I think so. We used it in one or two places. Okay. I don't have it on the top of my head, but it's definitely in one of the lecture notes. And then we have different relationships between the partial derivatives, so know how to move the terms around. And the biggest application of this one is, remember when we were talking about the relationship between volume, temperature, and pressure, you can write out, that's where we're getting, you can write out 6 pairs of partial derivatives. And those 6 partial derivatives are actually interconnect with each other. So that's why all those 6 partial derivatives ends up to be just 2 of them. And those 2 gives you the 2 coefficient that you can experimentally measure. So yeah, calculus is something that I'm not the best candidate to teach you calculus, but I really hope this course help you like refresh your memory on how to use these calculus a little bit. And if you are confused about these calculus problems, or you just don't know how to study, you can also leave a comment or send us a message. We'll give you some example problems to work on. Your textbook has some very good practice problems. Yeah.
Do you know if there's like any way that we could get like a solution manual? Because they only like do random selections.
I don't. But if you have like specific questions you want us to look at, you can send me an email and can check your answer. Okay, let's move on. And then equation of state. As we were saying, when we were saying equation of state, we're just using this equation to describe different relationships for a specific system. All right, so for ideal gas, you have the ideal gas equation of state. For van der Waals gas, you have a different equation of state because it considered intermolecular forces now in the van der Waals gas. Or for liquid and solids, now these are much less sensitive. Their volume are much less sensitive to like pressure. So they have a different set of equation of state as well. So the idea of equations of state is like, it's a function. For example, like a volumetric equation of state, it says a volume is a function of like T, P, number of moles, etc. for that specific system, gas or liquids or something. And when we're talking about the equation of state, we used calculus to find out in order to find the equation of state, you only need, well, to measure two partial derivatives. Or in this case, it's the thermal expansivity, or alpha. That's 1 over V times partial derivative of V over T at constant Pn. And also the isothermal compressibility. As a matter of fact, like what we actually care about is like the relationship of these different terms, right? So the thermal expansivity and isothermal compressibility, these are just coefficients that are easy to measure. Now you can easily imagine something like people are measuring the volume change with respect to temperature at different pressure, and you can measure the thermal expansivity. And also like isothermal compressibility, you can change volume change of different over different pressure at constant temperature. But it'll be by measuring those, it gives you information like something like how is your pressure change with respect to temperature, which is something that's not so straightforward to measure. All right, so the power of thermodynamics, and also like the reason we define these coefficients is we want to use these easy to measure terms in order to give us relationships of things that we do not know. Okay. All right, and at the end of chapter 1, we went over integral calculus. So like the differential calculus, I don't have too much to share for the integral calculus, just know how to set up the calculation and know what exactly integral calculations are doing. One of the useful strategy for solving your integral calculus is, for example, if we have like dx over dA equals to ax squared or something like that. Wait, not ax squared. Like, okay, so ab squared plus like bx, and you want to solve the integral of this process. You want to move the terms, so your dx goes with x and your a goes with a. So let's say dx equals to, and then you can take the integral on both ends to help you solving the problem. Now in this case, we want to move that x to the left, which, again, this one is not a very good example. I'm not very good at picking out examples. Yeah, let's do this. So now if you want to move that x to the left-hand side, you would divide x on both ends. And then you take the integral. You get x over 1 dx equals to ab squared plus b dA. And you take the integral to get an idea about what that looks like. So, I mean, that's just one of the very basic strategy of integral calculus. You move the terms x with x, a with a. Okay, any questions on chapter 1 topics? All right, sounds good. Moving on to chapter 2, we start by looking at classical mechanics, and that includes the definition of force, what is work, what is mechanical energy, that involves kinetic energy and potential energy. And then we spent some time talking about PV work. The most important equation we went over is so far as the change of your reversible work always equals to negative PdV. In a closed system, reversible work. And just keep in mind, work is a line integral. So again, the work on that PV diagram is the area below that curve. So for example, from 1 to 2, if we have a purple curve, then that is the work reversible for this purple path. Alternatively, you can imagine this go like this direction. And then the blue one will have a different number for that reversible path. We also went over heat and heat capacity. So heat capacity links heat and temperature. So one of the things I want to use this to quickly demonstrate is, well, what exactly is Q if we only know like CPR equals to dQPR over dt. So this one, if I'm moving the term dt to the left-hand side, we have CPR dt equals to dQPR. Right, so CPR might be a function of temperature. That's why we're moving it to the left-hand side. And taking the integral on both ends equals to integral of dPR dqpr. This one just becomes qpr. Or the other way to put it is like qpr equals to cpr dt. Now, for ideal gas, that heat capacity might be a constant, and if it is a constant, we can take it outside of the integral. If it's not, you cannot do that. And at constant pressure and constant volume, there are ways to define Cp and Cv. So these are the heat capacities that people can measure at constant pressure and at constant volume. And you can use these measured heat capacity at a later time, but know the definition of each heat capacity. All right. And then we spent a lot of time talking about the first law of thermodynamics. The important thing of the first law of thermodynamics is you have delta U equals to Q plus W, or you can write dQ equals to dQ plus dW for a closed system. Now I want to ask you a quick question, like why this one is a wrong expression for the first law of thermodynamics? Yes?
Because Q and W are not state functions.
Yes. So if you think about it, when we write it as delta U, what we're saying is this one is U2 minus U1, or U final minus U initial to make it more straightforward, right? So if we're writing it in this way, we're saying this one delta Q is Q final minus Q initial, but we don't have something called Q final or Q initial. Q itself talks about the process of that thermodynamic process. So that's why we only write dQ equals to, or delta U equals to Q plus W. Right, so do not write delta Q or delta W. It makes us very upset. And it will confuse yourself. You'll be like, I don't know how to calculate Q for a specific state because it's not in existence. And then we define enthalpy. So in this part, you want to, well, first of all, know the definition of enthalpy. So H, enthalpy, is by definition U plus PV. And then at certain scenario, for example, at constant pressure, we know that delta H equals to QP. And that's the physical meaning of enthalpy. All right. And in this case, I want you to go back to your lecture notes and know why these are true. We went over the derivation and the proof of these processes in class as well. Then for the Joule and Joule-Thomson experiment, we define the Joule-Thomson and Joule coefficient accordingly. So again, these coefficients are there because they give you a way to build connection between your internal energy and T and V, or internal energy and T and P. Now these will give us a way to measure how is your internal energy change with respect to like volume, or how is your enthalpy change with respect to pressure, using the Joule and Joule coefficient, Thomson coefficient, along with the heat capacity. All right, so these are the terms that, again, we proved together in class. So try to refresh your memory on proving these terms being true. Okay, and now let's do a problem together, which is the derivation problem. And again, we were talking about several times, it's like the purpose of thermodynamic is using these terms that we already like predefined or we already easy to measure to get an idea about what is some of the unmeasurable things. And here, in this derivation, you can also build relationships between these coefficients. Now let's look at this problem here, which is 2.35b, where we're trying to link what is your Joule-Thomson coefficient with the Joule coefficient, and also heat capacities or the isothermal compressibility. So I'll put this useful information here, and then let's do the derivation together on the board. You can do it on your own paper. I mean, we have different ways to do it. We'll see if my way works for you. And this one is like a proof, so you know you get it right at the end. So we'll see how that goes. All right. at the beginning, it gives you a hint, right? So read the hint and use it. It tells you to start by taking the partial derivative of P at constant T for enthalpy H. Yes?
Can you turn that light on? So
Oh,
we
yeah.
can talk one?
Shoot.
Thank you.
Working? Okay. Let's start by following its suggestion of taking the partial derivative of enthalpy over P at constant temperature. And now this one, we have the definition of H. So, definition of H is U plus P at constant T. And in this case, remember what we're using are the calculus like dxy equals to x dy plus y dx, or like du plus v equals to du plus v. So these are the calculus we're using to rewrite this relationship into, first of all, partial derivative of u over p at constant t plus p dv, dv over dp at constant t plus v times partial derivative of p over p at constant t. All right, so the relationship here is just using calculus. Now, some of the terms we already know we have it right. So for example, this one, this becomes 1, so this entire term becomes v. And this term here, the partial derivative of v over p at constant temperature, so that reminds us of the definition of the isothermal compressibility, right? So we have chi, by definition, equals to 1 over v times partial derivative of v over p at constant t, or we can write partial derivative of v over p at constant t equals to chi times v. And we plug this chi v in here, and this term becomes p chi v. With me so far? Yes. Yes, that's right. All right, so we have this term written out. And taking it together, what we have is partial derivative of h over p at constant t gives you partial derivative u over p at constant t minus p chi v plus v. And if we go back like just one quick page, we know that this term, the partial derivative of h over p at constant t equals to negative cp mu gt. All right, it also like sort of lead you in this problem, asking you to prove equation 2.65 again. So in equation 2.65, we know that this one is a negative cp mu gt. We can rewrite that here. All right. Now, the only thing difference between what we want and what we have right now is this term. Again, what we want to prove here is Cp, negative Cp mu Gt equals to V chi Cv mu J minus chi Vp plus V. So that's what we're trying to prove. And this is what we have right now. All right? And now the only thing different is we're trying to prove that the partial derivative of u over p at constant t equals to here, equals to volume times chi Cv mu J. Now we don't know what this partial derivative is, but what we can do is write this term out and see how it relates to this partial derivative using the definition of each of the coefficients there. So let's start doing it. So we have V chi CV mu J. And in here, well, V is just stays outside. That's just a state function. For chi, we have it equal to 1 over V times partial derivative of V over P at constant T. So that's our chi. And CV equals to partial derivative of U over T at constant volume. Mu J, or our Joule coefficient, is change of T over V at constant internal energy U. Right, so this one is just writing out each term by its definition. Now, some of the things will raise an alarm. So for example, this term here. Remember, we have the chain rule for these partial derivatives. So what we have is, well, if you write out everything at constant V, dt over dV at constant U times dV over du at constant T. That gives you -1. Or naturally, we can rewrite these terms to be equal to dt at constant V, dt over dV at constant U, and move this term to the right to be negative. Partial derivative of U over V at constant T. All right. And what we have here, coming back, is V chi CV mu J equals to, well, these V cancel out, we have negative. Partial derivative of V over P at constant T. And here we have another negative, so that cancels out. Partial derivative of U over V at constant T. All right. And then in this relationship, both of these partial derivatives are measured at constant T, or defined at constant T. So we can use the calculus to cancel out this dV term. So the calculus, what we're doing here is like dV over dr equals to dz over dx times dx over dr. So that's why we're canceling out that dV term. All right, and that becomes quite obvious. V chi CV mu J just equals to partial derivative of U over P and at constant T. And that's what we're looking for here to complete the proof. All right. How are we feeling? You see, it will only take like 7 minutes to work out this entire proof. Yes.
Would we get like a hint, just like get
Well, if
started?
needed,
Because,
like
I
for
wouldn't
example,
know.
in this problem, we'll give you the hint, right?
Yeah. Okay.
Like the only thing that you will need to know yourself is, for example, if you end up here,
Yeah.
and you don't know anything about U, you don't know what U is a function of, you need to know, like, you have to start from here and go backwards. Any questions? Yes.
Can you turn off the light for a second?
Oh, yeah. Wait, I actually don't know how to just turn off that one. Yeah.
That's okay.
Okay. You'll find the full derivation on the annotated note as well, so you don't have to write everything down. And then we have like 10 minutes. Let's finish our overview before we see one more example. Again, we went over some of the concepts, just half of your chapter 3. We start by the long definition for the second law of thermodynamics. And well, that's the Kevin Planck statement of the second law of thermodynamics. Just like read it and try to link it with some of the heat engine we talked about, so you know what that second law of thermodynamics is talking about. So basically what it says is you cannot transfer the unordered form of energy. So heat is a disordered form of energy. Work is a ordered form of energy. Now you cannot 100% transfer your disordered form of energy into ordered form of energy. And then we went over what is a heat engine, how do we define a heat engine, where with a heat input into the engine does work on its surrounding and output some, the leftover of its heat into a cold reservoir, and we define the efficiency of that heat engine in the process. We went over the derivation that the efficiency equals to 1 plus QC over QH. Now QC is the heat leaving the heat engine to the cold reservoir. QH is the heat input from the hot reservoir. Now QC and QH always have different sign, so your efficiency is less than 100% for any heat engine. Now, one of the questions your discussion worksheet has, which is a little bit interesting, also from your textbook, is, well, if you have a heat engine, a random heat engine, which one of these heat will you change to make it more efficient? That's something that sounds like a unapproachable problem. You're like, I don't know what that is. But if you think about it, when we're talking about these heat transfer, you can also link it to the temperature of your cold and hot reservoir. For the cold reservoir, the lowest temperature you can get is 0 Kelvin. It does not go any lower. But for the hot reservoir, well, we do not have an upper limit for how high that temperature is. So logically, it's more reasonable to raise the temperature for the hot reservoir rather than lower the temperature for the cold reservoir. I'll leave you to think about it. All right. Nevertheless, we then went over the Carnot cycle for ideal gas. And by the way, the picture for our course on Brewing Learn, that's also a Carnot cycle if you look at it. Now, a Carnot cycle is by definition a reversible cycle, consists of 2 reversible isothermal processes and 2 reversible adiabatic processes. Now, with that in hand, we can look at some of the properties, or, well, what is your delta U, what is your delta H, what is your temperature change, what is your entropy change for each step for your Carnot cycle, right? So, for example, in this case, when we're looking at the first one, the isothermal process, we know it is isothermal, and let's assume ideal gas. So some of the things we can immediately write down is that delta T equals to 0. So it's isothermal, so initial final temperature is 0. So that tells you your delta U equals to 0 for ideal gases. Right. Now, again, reading the table, from point 1 to point 2, this process, your volume increase, or you have W reversible equals to negative PdV. Now, your volume increase, your pressure is it's not a constant, but it must be a positive number. So in this case, what we know is that your work reversible must be a negative number. Your system is expanding. It does work on its surrounding. Now, for ideal gas, we can actually write out that integral because we know what P is. So using the equation of state, we have nRT, where T equals to TH over V dV. So you can actually calculate what is the work reversible. And using the first law of thermodynamics, we have delta U equals to Q plus W. So for the first step, although it is an isothermal process, but because you have a work reversible that is negative, your heat must be a positive number. All right. And for entropy, we have the definition of delta S equals to, ds equals to dq ReV over T. Now for the first isothermal process, if we take the integral on both ends, now T is isothermal, it's always at TH. So we have delta S equals to TH over 1 QReV. And we know QReV equals to negative WReV. And we have an expression for WReV. So you can also calculate delta S for the process between 1 to 2. All right. You can do that for every step along the Carnot cycle. And let's just do one more mental exercise. We're not going to do any calculation, but just know how to set up the problem. Now you can create your own cycle or your own PV diagram, imagining a thermodynamic process. So instead of a Carnot cycle, you can create just a random cycle. I dreamed it out yesterday. I don't promise like everything is accurate there. So for a dreamed up cycle, just try to calculate delta H, delta U, delta S for every state, and then Q and W for every process. All right, and this also involves like P, V, T, etc. for every state, and Q and W for every process. There are several different types of thermodynamic properties we went over. Now, the first one, we didn't tell you what it is. By just looking at the PV diagram, can you tell me what kind of thermodynamic process we have? Right, so that's an isobaric process. And from 4 to 1, well, that's isochoric, where volume is the same. Now, adiabatic and isothermal, we went over that in the Carnot cycle. For the isobaric, what we know about it? Now, what we have is P1 equals to P2. So the pressure stays the same. So assuming it's a reversible process, we can work out our W reversible. Now your pressure is the same. So we can take that pressure out from the integral. It just becomes negative PdV or delta V. Now this one is an isobaric expansion. So again, your system does work on the surrounding and you know how to calculate your work. For the heat here, it is an isobaric process at constant pressure. So what we have is QP. Remember what QP equals to? Delta H. And also, right, so we went over that derivation of what QP looks like. And if we know it is an ideal gas, you can also calculate the change of internal energy and consequently get what QP is. And we have, well, dS dQ ReV over T. Now, in this case, we cannot take that T outside because it's not an isothermal process anymore. So what we need to do, if we were to find delta S from 1 to 2, you're actually taking the derivative of from 1 to 2, 1 over T dQ 1 to 2. Right, because your temperature is not a constant anymore. You can't take it out from the integral. All right. For the adiabatic, well, we know plenty of adiabatic processes. Well, the most important one is Q equals to 0. And because of that Q equals to 0, we went over a derivation of like T3 over T2 equals to V2 over V3 at R divided by CVM. Now, CVM is the molar isobaric heat capacity. And if you don't remember where that comes from, the lecture note, we went over that. It's the adiabatic expansion of ideal gases. And, well, one more minute. So for the isochoric process, what we have is delta V equals to 0. So your work reversible equals to 0. All right, so your delta U equals to QV here. And for an ideal gas, in this case, from 4 to 1, your temperature increase right? So PV gives you the temperature of that ideal gas. So from here to here, your temperature will increase, and you know what the process is. And also, once you know what Q is, you can calculate for delta S, etc. So just like these kind of problem, I hope it gives you an idea about like what to do for a problem, like how to set up a calculation. Now, plugging number, that's a different story. But what I want you to know is how to set up the problem. And we do give partial credit. So if you set up the problem correctly, but you end up having the wrong number, well, chances are you'll lose 1 or 2 points, but you get the majority of it. All right, so show us your work. And make sure you bring plenty of scratch paper to write on your own notebook. We will also have 1 or 2 pages, but my exam is like printed on both sides. So if you do not have a scratch paper, you might run out of space. All right, so have a scratch paper for yourself to use. And that's it. All right, good luck.